Hello, everyone, and thank you for attending today's webinar, Intelligence at Scale through AI Model Efficiency. This webinar is brought to you by Qualcomm and is a continuation of our webinar series on AI. My name is Pat Lawler. I'm a staff manager in technical marketing at Qualcomm Technologies, and I'll be the moderator today. Before we get started, I'd like to go over a few housekeeping items. At the bottom of your screen are multiple application widgets you can use, including a widget to download today's presentation. All the widgets are resizable and movable. The slides will advance automatically throughout the event. At this time, we recommend that you disable your computer's pop-up blockers. This will allow the slides to advance automatically throughout the event. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A widget and then click Submit button. We'll answer questions after the presentation. Also, if you're experiencing any technical problems, please type your issue into the Q&A widget and we'll be glad to offer assistance. I would like to now introduce our two presenters for today. Timon Blackenvoort is a senior staff engineer at Qualcomm Technologies Netherlands BV and part of Qualcomm AI Research. Chirag Patel is a principal engineer at Qualcomm Technologies and also part of Qualcomm AI Research. Timon, please take it away.
Great, thanks for the introduction, Pat. I'm very excited to be here as the team lead of the neural network efficiency research that we're doing, to share a little bit of the AI research that we're doing to enable you to deploy your networks to many, many devices very efficiently. I'm only going to show a little portion of what we're doing, but it's still going to be cool to show off this work to everybody out there. So for a little bit of an agenda for today, I'm going to talk a little bit about efficient machine learning and how important this is for the community as a whole. I'm going to talk you through a little bit of the latest AI research that we're doing to make models more efficient, specifically centered on neural architecture search. And afterwards, Chirag is going to tell you all about the open source projects that we have to enable all of the research that we're doing to enable everybody to use that. So, of course, artificial intelligence is everywhere nowadays, right? That you can't buy a smartphone anymore without there being 50 different neural networks on them. And these enable all sorts of really cool use cases, like important things like smart factories, autonomous vehicles that really change the world around us. It helps with things like video conferencing, where nowadays neural networks are compressing video streams and making sure that backgrounds can be segmented out. And really, you can't buy a device anymore without a neural network in it. And one of the things that we often see nowadays as well is that the video use cases are becoming more and more important. So things like video monitoring, smart cities, conferencing, and self-driving cars all need video. And these workloads are generally very challenging because they operate on very high resolution images and they're always on. So every second there's many, many frames that have to be processed. So these networks also tend to be really large. And in general, as AI is progressing, we're seeing that neural networks are becoming bigger and bigger. So we have this fun plot that we keep updating every year. And recently as well, Google released a network that had more than 1.6 trillion parameters. So every year, the networks that are very accurate, that are beating state of the art, become bigger and bigger and bigger. And at this rate, actually in 2025, we're going to have neural networks that are roughly the size of the human brain in terms of parameters and neurons. Now, these networks are very, very big, but we still want to run them efficiently on devices. So as I mentioned before, we want to have these neural networks run on things like drones, on tablets, on watches, on VR headsets, on mobile phones, and in cars, etc. Now, generally, this is very challenging because the neural networks are big. They have to run in real time, so they have to run really, really fast. They're very frequently always on, so they are very power hungry. And they have to run on these very constrained devices. Many of the devices we want to deploy them to have to be very thermally efficient, so we can't have big batteries in there, and they have to be thermally efficient in terms of the heat leakage. And we have to make sure that the batteries stay on for a very long time. So if you run neural networks on your smartphone, you don't want the battery to drain and you have to recharge it every hour. And many of these devices have very restricted storage and memory capacity. So workloads are both big, and the mobile devices that we deploy them on are generally quite restrictive. And this power efficiency is important all across the space. So even if you run your neural networks in, let's say, a data center, you want to make sure these are efficient as possible if you run them on like a very large scale, just to save power costs. So in order to help a lot of folks with the deploying neural networks and making these more efficient, Qualcomm is doing a lot of research in this area to, on many different fronts, to make this deployment as efficient as possible. So one of the things we look at is, for example, quantization, where instead of running your neural network in the 32-bit float precision formats that's often used on GPUs, but to run them on, let's say, 16-bit or 8-bit or even 4-bit, which is a lot more efficient on device. Another thing we're looking at very frequently is something called compilation. So we can actually look at the neural networks and compile them in different ways to make sure that they run efficiently on device, that we actually change the graph and change the execution orders to do the optimization. We also look at neural network compression. So compression is about changing your neural network, pruning away useless parts, doing things like tensor factorization to make your neural network's layers smaller. So that helps them run more efficiently on device. And something I'm going to talk about later in the presentation is called neural architecture search, where actually AI algorithms help you design a neural network that's more efficient to begin with. So we really have like a holistic view of model efficiency research where we try to tackle all of the aspects of making your model more efficient. Now, one of the surefire ways to make your neural networks more efficient, and something that we've done a lot of work on, is called neural network quantization. So in neural network quantization, instead of executing your full model in 32 bits, we try to do it in 16-bit integer, for example. And then compared to 32 bits, if you run it in 16 bits, you can have like a 4 times energy and latency gain and speed up. So that's very significant. And we've actually seen our research that almost all neural networks can even be run in 8 bits and sometimes even in 4-bit weights, where we can get 16 times or even up to the point of 64 times faster neural networks, which is of course huge if you want to deploy your network on a mobile device. That's 64 times smaller. And we see that virtually all neural networks can at least be quantized with the proper tools to 8 bits, having a big gain in efficiency this way. Now the problem is this is not completely free because you always lose a little bit of accuracy while doing this. But we're doing a lot of research to kind of figure out, can we push the neural network quantization as far as possible so that you can still retain a very high accuracy with your network, but get all of these energy benefits from running something, for example, 8-bit. So one of the works we did in this area is called data-free quantization. This really asks the question, like, how can we do this process of taking your 32-bit network and turning it into an 8-bit network as simple as possible? So in this paper, we published a lot of methods that require no retraining and don't even need any data in order to optimize your network for quantization. And we see that some networks, like, for example, MobileNet V2, that break if you try to do 8-bit quantization completely, so you get 0% accuracy. With these methods, we can actually get most of our accuracy back while still keeping the full network in 8-bit, which is quite significant. Another work that we've recently released, it's called AddAround. So AddAround is about rounding the weights in the neural network to the nearest best value. So this is also a method that actually requires no training and only a little bit of data. And we see that with this method, without any retraining, we still can get some networks to go to even 4-bit weights. So you can have 4-bit weights and 8-bit activations, which is 2 times more efficient than 8-bit weights. And the accuracy drops that we see, for example, for MobileNet are roughly around the lines of 2 to 2.5% accuracy drops. But of course, your network this way is going to be 2 times faster, which is generally worth it. And for some use cases like object detection, we even see almost no loss in accuracy, although the network isn't 4-bit, which is quite surprising. And last but not least, we also have a paper published in Europe 2020, which is called Bayesian bits. And what this method does is it actually, while training, figures out which layer should be in 16 bits, which layer should be in 8-bit, and which layer should be in 4-bit. So while training your neural network with this method, it actually figures out the optimal set in this way to give you the best trade-off between your neural network accuracy and how fast you can actually run this on device. And with this method, we also get state-of-the-art mixed precision results on many different networks. So quantization is very good and very interesting. And I think in generally, this is one of the things that you definitely want to try to do to optimize your neural networks. But before you actually get to quantize your neural network, you have to figure out what is the design of my neural network going to be like. So we have many customers that come to us and ask like, hey, I have 50 different networks and I have 20 different use cases, and each of these networks I want to run on your device. how do I go about that? How do I optimize my neural network to run it efficiently on hardware? Now, this is pretty challenging because it's a very diverse set of networks, right? The neural networks themselves are big and they have to be optimized. The set itself is very diverse because there's many different tasks, many different use cases. And for each of those, there's many different networks that are being run on the device itself. But not only that, also the amount of devices that people are deploying to is very diverse. So, for example, you might want to run your neural networks on a low-tier mobile phone, or a mid-tier mobile phone, or a high-tier. So for each neural network, you have to adapt it for each specific hardware to make it efficient. And also, for example, your software might change. So if there's like an update in the kernel and it makes some certain layers more efficient, then you might have to like redo your searching algorithm, like your algorithm to optimize the neural network for each time that the software updates, which is of course very expensive. And this whole process of designing neural networks to be specifics for certain hardware is very costly. You either need a lot of engineers to do all of the hand tuning for this, which is of course expensive, but you also probably need a lot of GPU hours to do the fine tuning. So many companies have hundreds of GPUs to actually optimize their neural networks in this way, which incurs a lot of costs. So in the research community, there's a set of tools called neural architecture search, and they help you with this process. So neural architecture search tools help you with like essentially an automated way of learning neural network architectures that perform very well for a certain task for hopefully specific hardware. So what these methods do is they consist of essentially three parts. There's a search space. So you tell the neural architecture search algorithm what kind of architectures you want to search over. So how many layers it could have, like the types of layers that is being used, the type of activations that's being used, etc. And the challenge for the neural architecture search algorithm is to find the best architecture given the space that you have. To do so, it has a search algorithm. So the search algorithm looks at all the architectures that you've defined in your search space, and it tries to find the best optimal one out of that. And it does so based on an evaluation strategy. So you have to figure out for each neural network that you have in your search space, how accurate is it, and how fast does it run on your device. And of course, in the end, you want your search algorithm to find the optimal trade-off between the two. So which algorithm runs very efficiently on the device itself and is highly accurate. And it tries to find the best Pareto optimal version of those. So these tools are pretty great in order to help you actually design your neural network to be more efficient on hardware. But many of the current solutions have a lot of drawbacks. So in order to get a very high accuracy and get things to work very well in your hardware, you need to make sure that you can search over a diverse search space. So you need to be able to search over things like attention mechanisms or activation functions or different types of blocks. And many of the current neural architecture solutions actually don't search very well over this. So in order to change, for example, the activation function, you would have to rerun your whole algorithm, which is very expensive. There's also many of the algorithms that do have a diverse search space, they would incur a very high cost. So you would have to train for 40,000 epochs in order to get one network, which is incredibly expensive. And there's no method that finds a really good balance between the two. So something that has a diverse search space, but has a low cost. And many of these neural architecture search methods also don't scale very well to the different scenarios I sketched. Like, for example, if you have a different software version or different types of phones. So many of the algorithms would have you repeat the whole training phase of this neural architecture search method for each target device. But of course, if you have 50 target devices and your software changes, that can be very, very expensive very quickly. And many other methods also have unreliable hardware models, meaning that they either use a surrogate measure. Let's say, for example, we count the amount of parameters or the amount of flops and optimize for that, which of course does not mean speedups on the device itself. Or they would have you train a differentiable cost function that's also not a perfect representation of how efficient the model would run on a device. Now, in order to counteract that, we created a neural network architecture search method called DONA, Distilling Optimal Neural Network Architectures. And this is essentially an efficient neural network architecture search method that takes the hardware in the loop. It finds you a whole set of Pareto optimal architectures in terms of the accuracy and the latency at a very low cost. So the core essence of the method is that you start with a oversized pre-trained reference architecture. So let's say you want to do neural network like image segmentation. then you would start with a big segmentation network that you know works very well for your task. And the DONA method will then optimize that network for you to find a set of optimal methods in terms of the accuracy and the runtime on device. Now, the benefits of the DONA method is that it counteracts all of these problems that we've seen before. So it actually allows you to search over many diverse things like different activation functions and attention mechanisms. It's also pretty low cost. So at the cost of roughly training 10 networks, that's the startup cost that this network has. And it's very scalable. So there's a little bit of a startup cost in the accuracy method first, as you'll see later. But afterwards, finding an optimal network for different devices is very cheap, and you can do that within a day. And we also have the actual hardware device in the loop. So we have reliable hardware measurements, and we kind of use the metrics as if it would actually run on the device itself, which is very important to get good, accurate models out. So our paper has all the details, and you can look it up on arXiv later. But I want to quickly run you through the algorithm a little bit to give you a bit of a feeling of what this looks like and what the method does. So as I mentioned, you start with a oversized large reference architecture. So after you've done all of the design and make your neural network work for the task at hand, you have a big neural network, and that's what you feed into this algorithm. And then in the first step, we kind of define the search space. So what do we want to search over? So what does it look like? So there's on the top, your big reference architecture. And then the smart thing of this method is that we chop it up into little blocks. So in this example, we chop it up in the blue lines. And then the network consists now of 5 different blocks that we can optimize for separately. So there's a stem, 5 blocks, and then the head. And for each of the blocks, we'll optimize. And then for each of the blocks, you can actually define what your search space is going to look like. So what is the kernel size going to be? How many layers would we have within that block? Are we going to use attention mechanisms, yes or no? Or what kind of cell types are we using there? Anything that you want, you can actually add to the search space there. And for each of the blocks, we'll independently optimize the blocks for that search space. So after we've done that, we do the blockwise knowledge distillation step. And the idea of this step is that we find a accuracy model, meaning that for each of the blocks that we chopped it up into, we have different options. And for each of the different options, we want to figure out how good is that block and how accurate is the network in the end going to be. So on the left, you'll see the block library, which you create. So for each of the block options, we really quickly fine-tune the block with blockwise knowledge distillation. By doing so, we get 2 things. We get the pre-trained weights. So these are pretty strong, good initialized weights that could be plugged into the original network and work. And for each of the blocks, we'll get a quality metric. Like how accurate is this block in representing the loss at the end? This is done pretty quickly for like the whole search space, and that can be as broad as you want. And afterwards, we also make an architecture library. So by subselecting random blocks, we compose them into like 20 to 30 neural networks, and those are trained end to end. So for those neural networks that we've sampled with the blocks, we know what the accuracy at the end of the network is going to be. Now, once we have the block library and the architecture library, we can make an accuracy predictor. The accuracy predictor basically tells you if I pick block A or block B or block C in each of the slots, how accurate is this neural network going to be? And that's very important because this accuracy predictor we can later use, we can later reuse a lot of times during the search. So in the step afterwards, we do an evolutionary search with the actual hardware in the loop. So you can actually use a mobile phone in the loop, for example, to do the search on. And then what we get in the end is this blue curve, which is essentially a curve indicating the whole set of Pareto optimal networks that are the best, give you the best trade-off between the latency on the device that you plugged it into and the predicted accuracy. So we have this evolutionary search algorithm that we use for this. And as I mentioned, it has the actual hardware in the loop, and it uses the accuracy predictor that we trained before. So this is very cool because this accuracy predictor can now be reused for any time you deploy something for a different hardware, because the accuracy of the network doesn't really change depending on the hardware that you deploy it to. So the benefit of this is pretty cool because the accuracy predictor is pre-trained. This whole step only takes roughly 1 day with one measurement device. So running the evolutionary algorithm, if you want to deploy it to a new chip or like to a new software version, you only have to rerun this step for roughly a day. And also, as I mentioned before, because we use the actual hardware in the loop, of course, the search itself is going to be very accurate and very representative of the actual device that you want to deploy to. And lastly, you can actually pick one of the neural networks and you put it to optimal front. So let's say you want one at 50 ms latency. You pick that network that's in that set, and then you can quickly fine-tune this. And because all of the blocks that we had before are already fine-tuned, instead of training for like 450 epochs from scratch, you can actually see in the algorithm that you can train your neural network for 15 to 50 epochs and get state-of-the-art ImageNet, for example, accuracy by doing this training. So in the end, you're left with, for one specific device, for a specific like latency that you want, you are left with an optimal network. So you see that, for example, the blue curve that we have here, that's like the set of optimal networks that we have. You pick a few of those, and those you fine-tune with blockwise knowledge distillation in this method. And that turns you into these confirmed accuracy points, as you'll see in the next slide. So in the next slide with the results, you'll see like the blue curve indicating like the set of all networks that we find, and then the blue dots are going to be the ones that we actually confirmed and trained end-to-end to get the actual proper accuracy. So looking at some results, we find that our DONA method finds state-of-the-art networks for many on-device scenarios. So if you look at the flops all the way on the left, our networks that we find are actually equal or better than many of the other methods out there in research. So you see methods like once-for-all networks, OFA, DNA, ResNets, different types of mobile nets, and different other methods like agnostic that all optimize for flops. And our method finds networks that are either equal or better than those. But our method shines even more when deploying things on device. So if you run things on like a desktop GPU, for example, as you see in the second picture, or if you look at the third and fourth picture where we run things on a Qualcomm chip on the GPU or on the the Hexagon 780 processor, that's the AI accelerator that's in the chips nowadays, we can see that we can find networks that are on average 20% faster at a similar accuracy. So you can see that these networks are really optimized for the hardware target that they're deployed to, which is kind of cool. And if we compare this method also to the other methods in literature, we see that methods like once-for-all networks or DNA, OFA and DNA in this table, they can run it pretty efficiently, but they lack a diverse search space, and that hurts them in the accuracy in the end. And some other methods that have a very diverse search space that they can search over, like agnostic, although the search space is really big, they have a really high cost. If you look all the way on the right, there's a lot of epochs that you have to train these networks for in order to make them work very well. And our DONA method basically gives the best trade-off between both of them. So we have a very diverse search space that gives you accurate models at a very low training cost. And one of the really nice parts of this DONA neural architecture search method is that it generalizes really well to models that we've never seen before. So applying the same method that we applied on standard image classification benchmarks, we can apply this on object detection networks out of the box and see that we can also get optimal networks in that setting. Or even something more exotic, like vision transformers that were released recently. Out of the box, our method works there, and we can actually see that if we start with one of these VIT or DIT base methods, that we can find a whole Pareto set of optimal curves that optimize the network for on-device performance. And although they're still slower than some of the image networks that we currently use, we can still see that the neural architecture search method works on even exotic networks that you might want to deploy. So all in all, if you look at it from a user perspective, as I mentioned, I think the key takeaway is you have your big network that you want to deploy to many different scenarios, many different phones with many different software settings, etc. Then with the DONA method, you can go through this 4-step pipeline from A to B. The first part is making this blockwise knowledge distillation library, and that's equivalent to the cost of training 10 networks from scratch. It's pretty cheap. Afterwards, you can do this evolutionary search on device, which takes roughly 1 day per use case that you want to run it on. And afterwards, you fine tune for a little bit to make the network work well in terms of accuracy. And out of the algorithm comes a set of Pareto optimal network architectures, and you can pick ones that you actually want to use to deploy. So I guess that's the key takeaway of our neural architecture search method. It shrinks your big neural networks for many different hardware devices, taking actual user constraints into account. So it enables scalability and allows models to be easily updated after small changes. It works out of the box on many different architecture types, and we get state-of-the-art performance on standard image classification benchmarks. Now, essentially, what our whole team is doing is making all these research methods and publishing papers on this to all of the top-tier conferences. But we're also very dedicated to getting these tools and these methods out to the general public and commercializing and open sourcing many of these tools so that everybody can use them and everybody can deploy the neural networks efficiently to device. And one of the important parts of this is our AI Model Efficiency Toolkit, which is has many of the quantization techniques in there, many of the compression techniques that our research team devised, and brings this out to the public in a very professional and efficient way. And Chirag Patel will talk to you all about the AIMET toolkit and about the model zoo that we have attached to this, which has a lot of quantized neural networks. So thank you all for listening. I hope you found the neural architecture search part of this presentation interesting, and I'm looking forward to the questions later. Chirag, perhaps you can tell us a little bit about AIMET and the AIMET Model Zoo.
Thanks, Timon. Thanks for the great presentation on our innovations on the NAS front. So, hello everyone, I'm Chirag Patel. I'm going to talk about our open source projects, how we bring our model efficiency research into practice for everyone to get benefit from. So we have AI Model Efficiency Toolkit, or what we call AIMET, and AIMET Model Zoo open source projects. Like we know, model optimization, especially quantization compression, is very challenging, and it's not straightforward. We see a lot of folks struggle on this front. So with these projects, we want to give powerful tools to everyone, whether you are a sophisticated practitioner or starting new. With these tools, we want to enable model efficient AI for different use cases. And I'm going to go into more details on the AIMET and AIMET Model Zoo. So AIMET is a project by Qualcomm Innovation Center. It's open sourced, available on GitHub. In a nutshell, AIMET's goal is to make AI models small. It is a library of state-of-the-art compression and quantization techniques. Like essentially, the way it works is you have a PyTorch or TensorFlow trained model. You can plug in AIMET and get an optimized model out and deploy on different targets, smartphones, IoT devices, and many other devices, and get the best performance in terms of accuracy, latency, and power. And the whole idea is to make the flow very easy and for anyone to use. So AIMET has a rich set of features. Timon briefly mentioned some of the features already earlier, and I'm going to describe. So on quantization front, we have what we call post-training techniques like data-free quantization, AddAround, and we also have fine-tuning techniques like quantization over training. And we have shown that these techniques provide state-of-the-art performance for integer inference. And even AddAround like techniques push the envelope further for inference. On the compression front, we have tensor decomposition techniques. You have a 3x3 tensor. You can break it down into the simpler 1x3, 3x1. And we also have channel pruning techniques. Like for example, in a convolution layer, some of the channels are redundant. So we can remove some of these channels and make the model more efficient in terms of memory or compute. And we have shown that like for popular models like ResNet 50, our compression techniques can reduce the MAC multiply and accumulate required by 50% without significant degradation in accuracy. So all these features provide rich benefits. Like quantization clearly reduces the memory bandwidth requirement or the storage requirement by instead of the floating point model, you can store the weights in lower precision 8 bits and get power as well as memory benefits. The best part is like we have made it very easy to use. Like that has been a big focus for AIMET. Like all these techniques are, though they are complex, you can read the papers from time and steam, but we have wrapped it up under AIMET in a very user-friendly manner. And to just to give you an idea how that works, right? Like this is a high-level architecture for AIMET. So we have the model optimization library, which contains all the algorithms for quantization and compression. And AIMET works with TensorFlow PyTorch. So you can take in a PyTorch or TensorFlow model, and after the optimization, you again get back the same PyTorch or TensorFlow model. And this way, one can seamlessly integrate into the existing pipeline. So the workflow essentially does not change. It becomes much more like a integrated workflow with the existing user pipelines. And at the same time, like under the hood, we run very complex algorithms, but the APIs that the user needs to call are very simple. Like with 1 or 2 API calls, you can get a post-training quantization done and compression done as well. So let me talk a bit more about the data-free quantization that we have in AIMET. So, and that is really a cool part, right? Like the papers are out there, but then what we do, we actually bring that research into practice, and anyone can go download AIMET code and use it. So what data-free quantization does, like often what some of the models we see, that for example, in a convolution layer, the weights across channels will have very different dynamic range, and the quantization becomes difficult. With the data-free quantization technique, we equalize the weight ranges, make the whole model more quantization friendly. And then we also have what is called bias correction. Like with quantization noise, there is a bias introduced in terms of the output of the layer. We correct that because we know what is the quantization error introduced when we quantize the weights and try to improve the performance further. These different subcomponents, like they are handled very easily by AIMET, and at the end you can get a quantized optimized model, and you can see the performance numbers at the bottom, right? Like for 3 of the popular models, MobileNet V2, ResNet 50 or DeepLab V3, we see very good performance comparing to FP32. The drop in accuracy is less than 1%. So taking it further, like we have another technique called AddAround. So typically for quantization, nearest rounding is done, but we know we have shown that nearest rounding is not optimal. So what AddAround tries to do, it tries to find the best rounding for a great tensor. And our results show that it can give great performance not only for integer 8 models, but even on integer 4 models. Here we are highlighting one particular like example use case for object detection in ADAS. You can see on the table on the left, like the performance mean average precision for FP32 model versus a baseline quantization versus AIMET AddAround quantization. So with the baseline quantization, the performance is very poor, like 49.85 MAP versus 82.2. While with AddAround, we get performance very close to FP32. And as one says, right, picture says 1,000 words. On the right, you can see qualitatively what is the performance benefit of it AddAround. Like on the top, you have the intent baseline quantization performance. You can see like the cross marks in red, like with regular quantization, some of the objects are not detected. The bounding box is completely missing, for example, for the red car here in the center. And some of the cars at the back are like misclassified. Their labels are like van or truck, even though they are actually cars. But now if you look at the bottom, so where we show performance with AddAround quantization, it's pretty picture, right? Like you see all the bounding boxes properly, all the vehicles are correctly identified in terms of their class. And this shows really the power of the AIMET techniques that we have. And because of this, right, like what we have seen good adoption by AIMET across like mobile OEMs, ISVs, and other developers. One extremely popular and powerful application is Snapchat. Snapchat needs no introduction. Like it is a global phenomenon with millions of users every day uploading like billions of snaps. The device camera is essential here. Like you create lenses that give fun and engaging experience. The lenses track the user's face in real time and morphs it, applies different style transfer effects, and morphs the user's face in a real-time manner, right? So clearly there is AI running behind these lenses. The neural network performance is critical for on-device to ensure that we have a seamless experience when the user uses the app. So typically we want to run all these neural networks at very high frame rate, more than 30 FPS, and that's where AIMET comes in. AIMET helps make it run efficiently, real time on the device. So the user will experience a very seamless and very real time performance. And what this gives is under the hood is better performance, but at the same time with reduced power consumption because the models are optimized for fixed point inference. So this is truly wow, shows how much benefits the AIMET can bring, and also our research is actually making impact in real world applications. So taking a notch further, right, AIMET is a library which has all the algorithms, and then you can go and download the code, apply on your models. We have taken it step further, we have actually released Model Zoo as well, what we call AIMET Model Zoo, with a collection of pre-trained 8-bit quantized models covering various popular use cases, image classification, object detection, semantic segmentation, and a lot of other categories. And it basically has a bunch of models, optimized for 8-bit inference. Along with the models, you can easily go and download the models from our GitHub page, but we also provide recipes or the example scripts. So how we actually quantize these models to get best performance, and that recipe can serve the user for their own models, right? So along with the AIMET, we give powerful tools or examples so that any user can use it for their workflow, for their models, and get the best benefits in terms of power, performance, and latency for taking the use case to the end device. And often, as we said, right, with quantization, the question comes up naturally, though, how much accuracy did you lose? What was the performance? And we have shown through this Model Zoo that we can quantize a lot of the models, like on the TensorFlow side or PyTorch side, with very good accuracy. You can see, for example, just to highlight few particular examples, let's focus on the PyTorch side of things here. EfficientNet Lite, a popular classification network, we see less than 1% drop in accuracy with integer 8 over FP32. Similarly, for challenging tasks like DeepLab V3, we have good performance, super resolution. In terms of PSNRs, you see good numbers here. So across the board, right, with the right side of techniques that we have in AIMET, you can quantize the models and get good accuracy. To stress the point further, this is a visual example of one of the model that we have, DeepLab V3 Plus model in the Model Zoo. Here we are, the task is to segment people. On the leftmost figure here is the FP32 segmentation performance. You can see both the people are segmented. You see a blue tint, which is the segmentation map on both the people here. But now if you look at the rightmost figure, you can see the foreground person is properly segmented. This is the baseline quantization. But the person in the background is not segmented. The segmentation map misses out this person. And that shows the limitation of baseline quantization technique. But in the middle, you can see, with the AIMET quantization technique and what is actually the optimized model available in Model Zoo, the segmentation performance is very good and almost comparable to FP32 model performance. So I hope with these examples, we convince you to use the AIMET Model Zoo models and even try out our quantization recipes and use AIMET techniques. And I'm sure you will get good benefits with this. So I would encourage everyone to please visit us on our GitHub pages on the AIMET and AIMET Model Zoo. Feel free to contribute. We welcome contributions. We have a growing active community on the AIMET side. We also continue to bring new features as we go along, like AddAround feature will be coming soon. We bring in different quantization techniques as well, and we continue to, we'll go and bring new features as we go along. So, and we welcome contributions from the community as well. We want active engagement, close collaboration with the whole community. So with that, I'm going to conclude. In a nutshell, we highlighted that AI model efficiency is crucial if you want to make AI ubiquitous, especially on the edge side where power is a concern or memory and other requirements are very tight. We need a model efficiency to be handled properly. And Qualcomm is at the forefront of leading the AI model efficiency research. Timon's team here does awesome work in terms of the quantization, compression, network architecture search that we presented on the DONA side. And at the same time, we bring this research into practice. We enable the broader community through our open source projects. And we hope with these open source projects and our innovations, we can move the industry forward towards fixed point inference, more efficient edge inference, and make AI happen at large scale on the edge side, and also at a lot of other places. With that, I'm going to hand it over to Pat, and then we'll do Q&A. Thank you, everyone.
Great. Thank you for the great presentations, Timon and Chirag. As a reminder, if you have questions related to the material, please submit them using the Q&A widget. We've already received quite a few, so let's get right at it. So first question, I think, Timon, this one's for you. For Donna and Met, if I want to optimize for power rather than latency, what is the training cost, assuming that I have the accuracy model already created?
All right, so the moment you already have your accuracy model in the DONA method, most of your work is already done. So if you want to optimize your neural network for a different target, essentially, right? Instead of latency, you want power. You just have to rerun this evolutionary search once. And as I mentioned in the slides, that roughly takes us a day with one device. So yeah, optimize for something new takes a day.
Great, thanks, Timon. Next question. This is also for you, Timon. So for Donna and Met, how do you find the model on the Pareto optimal curve that corresponds to a specific latency? And also, how smooth is the curve?
Okay. So essentially, once you have this Pareto optimal curve, you'll have a whole set of networks that's on that line, that blue line that I showed you before. So if you want to have a network that runs at like 100 ms, so 10 frames a second on your phone, you just pick that network that's in that vicinity. And that curve itself is generally very smooth. So we find many networks that are on the Pareto optimal curve. So there's a pretty high resolution. Like if you want 100 milliseconds or 105 milliseconds or 110 milliseconds, there will be networks there that are very close to that runtime.
Great, thanks, Timon. Another one for you. You are popular. So for Donna and Met, what is the cost if I want to test things like add a new block, make a driver change the Qualcomm Neural Processing SDK, or use a different Snapdragon SoC? What do you ever need to retrain for the accuracy predictor? So a lot to unpack there.
Yeah, that's very interesting. So you actually mentioned two things, right? Like if you want to add things to your block space, to the like, let's say you want to try a new type of block, for example, right, in your search space, then you have to start retraining those blocks. And that's very quick. It's roughly 1 epoch of training per block that you add, but that's still a little bit of a cost. That's part of that initial fee. But again, any of the new targets that you have, so if you change your software version, or change your driver version, if there's like a very significant change there, it just goes back to the accuracy model already exists. The only thing you have to rerun is the evolutionary search, which takes roughly a day.
Great, thanks, Timon. I think, Chirag, this one's more for you. How has the traction been for AIMET? What feedback have you gotten from the community?
Hello, Pat, can you hear me?
Yes.
Yes.
Sorry, somehow I had an audio problem. I'm not sure. So can you please repeat the question? I can answer.
Sure. How has the traction been for AIMET? What feedback have you gotten from the community?
So yeah, I think we have received very positive feedback from the community. We see a lot of Q&A on the GitHub, as well as like separately we get emails. Even we had a presentation recently in TinyML. We got very good reception there. in terms of adoption, right, as I showed, we showcased one use case here by Snapchat. We are working with a lot of other partners, OEMs and other ISVs, who are also seeing the benefits from AMET. So overall, I would say we have seen positive feedback. We have seen encouraging signs, and that's why we are continue to improve and bring more and more features based on the feedback we have received.
Great. Another good question here, probably for both of you guys. What's next for AI model efficiency in terms of both research and open source, and what do you see as the best opportunity?
I think this is a really cool question. Perhaps I can address the research part first, and then Chirag can mention the open source part. I think one of the really cool new challenges in model efficiency is something called conditional computing, and where essentially you want to like turn parts of your network on or off depending on what you're seeing. Like as a person, like your brain isn't always firing all the time, right? Depending on the context, you want to like figure out some features. Like if you're cooking, you want to be looking for knives or for potatoes or whatever. But if you're on the road, you don't have to calculate the features for a potato. So one of the real cool things I see as a future of AI model efficiency research is abusing like this conditional computing. So some parts of your network are on or off depending on the context that you're looking at. I think that part is very, very exciting. Chirag?
Yes, so I think on the open source side or AMET, like whatever innovations we have, we'll continue to bring along into the open source pipeline for everyone to benefit. For example, the AddAround feature that we highlighted results, we hope to bring it soon for everyone to use on the open source. As we go along, we'll bring more features on quantization front and other model efficiency features in future.
Great, thanks, Chirag. So yeah, lots of questions coming in. So next one, probably either of you guys can answer, maybe Timon. Have you experimented with running AIMET after DONA? What reduction is still possible after NAS? And how do you aim to close that gap?
Yeah, that's a really good question. So what we've tried already is to apply our quantization techniques on top of the DONA neural architecture search. You can actually, if you look into our paper in the appendix, the new paper version that's on archive, you'll see that there's some results there with quantization in the loop as well. So instead of doing the neural architecture search first and then applying the quantization on top of it, we actually do the quantization in the loop, but we also do the quantization after the floating point search. So we tried both, and both seem to work very well. So you can just do the quantization and the ranking of which network serves better in floating point. That same ranking holds after the quantization as well. So the two tools essentially work very well together. We haven't tried the compression yet. That's another potential research topic. Like how far are the neural architecture search methods still compressible? That's still for us an open question.
Great, that's really useful for people trying to build these networks.
Yes. Yeah.
So next question, introductory question. So maybe Chirag, you can help with this. I'm just getting starting to work on training on Snapdragon devices, and I'm wondering if you guys have any advice on accessing documentation or examples to get started on this task.
So I think the question is not completely clear, but we have a lot of documentation. Like for example, if you go to AIMET GitHub pages, we have a dedicated section on documentation. We have tutorials as well if you want to do quantization or compression. And then separately for Snapdragon device, there is on the QDN network, there are additional documentation on Snappy itself. So I think, yeah, please visit our GitHub page and you'll see pointers there.
Yeah, that's SNPE, so the Snapdragon Neural Processing Engine, which is essentially the software that you can use to take your neural network, either in an Onyx form or in like a TensorFlow form, actually run it on a Snapdragon device. So if you Google SNPE with Snapdragon, I think you'll find that.
Yeah, thanks guys. It's actually the Qualcomm Neural Processing SDK, but yeah, you'll find it. Just search for that. Next question. It's kind of on how generalized AIMET is, and does AIMET Model Zoo deployment Is it supported for ARM chipsets? I think
so, yeah, I
this
can
question
take that.
maybe. Yeah, please do.
So yeah, thanks for the question. We have not directly tested on the Raspberry Pi and other devices you are mentioning, but there is no reason for think of this way, like what the AIMET produces is a PyTorch model and optimized with the optimized weights. And now you can take it to any target you want, right? So AIMET is supposed to be hardware agnostic. All the model optimization techniques can be used to get the best model out and deploy on the end target. So it should work basically. There is no reason for it not to work.
Okay, another quick one maybe, or I can answer it. A lot of questions around where can we access the DONA study material. So one is these slides, but the best resource currently is the actual paper. So it was in one of the slides, the name, but if you just Google for DONA and NAS, you'll be able to find it on archive. So Timon, here's a good question for you. Given that DONA takes into account hardware in the loop, does this depend only on the accelerator's operating mode?
Yes, essentially, like so if you want to do a search for a device, like you actually have the actual device in the loop, and generally, for example, on a Qualcomm chip, you might want to set the operating mode or the efficiency mode. So, like, do you prefer something like low energy but slower, or something very fast but consuming higher energy? And if you're running the neural architecture search, you just set that on the device itself, and then do the search with that in mind. And because we're using the actual device with the actual setting, your neural network will optimize for that specific setting. Now again, like it might be that you might want to run your neural network for 3 different optimization settings, right? And have 3 different versions of it. Or perhaps you want to optimize it for a combination of all 3 settings. That's something you can also do, because you can just either rerun the search 3 times, which is very cheap, or you just have a combination of the 3 metrics that you combine into one metric and optimize for that. So really anything you want to do with the performance settings, you can set yourself and do the hardware search on top of that.
Perfect. Here's a good, I'm seeing a number of these questions, so maybe it's good to clear it up. It's asking, does AIMET work on Snapdragon 865? And just to make it more general, does it work on 855, Snapdragon 888, and even other chips? I mean, non-Qualcomm chips. I think we should clear that up for the audience.
Sure.
Yes, the answer is resounding yes. It should work on all the platforms that Pat just mentioned. And if at all you run into issues, please send us reach out to us through the GitHub page or the email that we have. We'll be glad to assist.
Here's a more research and interesting question, maybe for you, Timon. Is there any performance data for Int8 or Int4 results?
For Int4, yes. I think the most results that are publicly accessible that we have can be found in the AddAround paper. So that's the adaptive rounding for neural network quantization paper that I mentioned. And there's a table with Int4 results that we have that's publicly available. So please check that paper.
Great. I think another thing we should probably clear up, I'm seeing some questions about this. Is it correct that DONA only works with Qualcomm hardware?
That's a great question. No, like DONA works with any hardware. So because we have the actual device in the loop, it doesn't matter if it's a Qualcomm Snapdragon chip, or a NVIDIA GPU, or a CPU, or, as I sometimes jokingly say, a potato. So if you want to optimize your neural networks to run on a potato, you can actually do that, because the method itself is completely agnostic of what hardware you're targeting. So yeah, for any hardware that you want your neural networks to optimize, you can use the DONA method.
Great. Yeah, I'm glad you cleared that up. Next question I see is, can we combine DONA and AIMET in a single project? It's probably still at the research stage, but I guess Timon?
Yeah, as I mentioned, I think before as well, I think the large part of AIMET here that we've tried to apply on top of DONA is the quantization tools. And we see actually two things. If you're within a search space, so if you have fixed, let's say, your squeeze and excite and your activation functions, then you can just apply on top of that the normal quantization tools that we have in AIMET, and then the models that we optimized before quantization are just still going to be the optimal ones after quantization. Now, if that, so if you do want to change like your switch functions and your activation functions within the network, there's a slight discrepancy with how well those things can be quantized. Like switch functions are more difficult to quantize, for example, than ReLU functions. And in that case, we can actually run the quantization in the loop with the DONA algorithm. So yes, they can totally be combined, and both quantization and neural architecture search, of course, work together to create the most optimal networks.
Great. Here's some other quick ones, hopefully. Does AIMET also support a TensorFlow Lite workflow and libraries?
So we don't directly support TensorFlow Lite workflow, but we do support TensorFlow. So you can optimize model in TensorFlow and then take it to TensorFlow Lite, right? That should still work.
Great. Can AIMET output Onyx models?
Yes, we do support export of Onyx models. Yeah, and it's a simple, like again, API where you say model.export or the command like that, and it will export the Onyx model.
And then maybe another one related to just what does it support? Will AIMET support TensorFlow 2 APIs as well? You point out.
Very good question. Yeah, so that's why on the roadmap, and we hope to bring TensorFlow 2.0 support in near future.
Okay, another good question, maybe just to point it out. Someone's asking for tutorials. So they're saying AIMET looks great. Would you be able to create some tutorials how to deploy models from AIMET Model Zoo to PyTorch or TensorFlow?
I think so. We already have some example recipes, but yeah, we can take a look into the request. If there is specific ask, we can definitely take a look and see how we can help. So please send us a request, and we'll be glad to help as much as possible.
And here's an interesting, I know you guys are focused more on the research, but maybe you have some insight. What would be a typical allowable accuracy drop in quantization or model compression for a commercial application?
I think this is an incredibly interesting question, and I think it really depends. Sometimes it's barely any accuracy drop is okay for somebody. So specifically in self-driving car scenarios, for example, people often request us that there's no change in the model output or barely any change. But sometimes it's actually fine to have like a couple of percent even drops in accuracy, as long as you get a lot of model efficiency back from it. And one of the things people don't always realize is that very frequently, you could take your neural network that you have, increase the size of it a little bit, and get higher accuracy in your task. So if you think like, look, 1% drop in accuracy for an 8-bit network is too much, you can always compensate for that drop in accuracy by making your model, let's say, 10% bigger. So make your model 10% bigger, then quantize it to 8-bit, and it's going to have exactly the same accuracy as it had before. So you can counteract some of the quantization effects by making just your model bigger, but it's still getting a lot more efficiency out of it in the end. Because 8-bit is just so much more efficient than 32-bit that it's almost always worthwhile running an 8-bit.
Great, thanks, Timon. We're just about out of time, but I just saw this question pop up, and I think we should answer it because it's very important in terms of NAS. So, Timon, you can answer this one. In DONA, is there a particular reason why you measure latency in the loop instead of using a latency predictor?
Yeah, I think this is really good. So essentially what we've looked at before is can we actually make a latency predictor for our hardware target, right? And to a certain extent you can do that, but it's often very inaccurate. You get differences of like 10 to 15%. And you get these difficulties because like some niche cases where your optimizer or your compiler or your kernel is something weird, that's very difficult to take into account into a latency predictor. And then if your hardware changes, you have to like retrain your latency predictor, and that's very expensive. And the fact that the latency predictor is so inaccurate also means that the networks that come out are very inaccurate. And we're getting these gains of like 20, 30% faster networks, but if that's being reduced by like, let's say 15% because your accuracy, like your latency predictor is not accurate, then you're actually foregoing most of the benefits you're getting from NUTs. So using a latency predictor is generally not a good idea for neural architecture search, and you're better off, way better off, just actually using the device in the loop.
Great, thanks, Timon. I think that's a good question to end on. So on behalf of Qualcomm and our presenters, thank you for joining us today. This webinar will be available on demand. You can download the slides, and I hope you have a great rest of your day. Goodbye.
Thank you, everyone.